Okay, these are the 7 points I'll go through when I summarize this chapter, discrete random variable. First thing I would like to say, what is a random variable? Let me give an example, okay? If I tell you x is the score on a random toss of a fair die, x is the score on the random toss of a fair die. Is x a random variable? Yes, x is a random variable. Why? Because you can see carefully here, x can be 1, 2, 3, 4, 5, or 6. There are 6 different possible outcomes. There are different possible outcomes. Every time you perform the experiment, it can have a different outcome. It's a random variable. Yeah, random variable. If I tell you y is Mr. Lim's height on 1st May 2020. Now it's passed. There is a particular value. You may or may not know what is the value of y, but y is a constant. You may not know the value of y, but y is a constant. You may not know Mr. Lim, but something is passed. There is only one value you can take. Y is a constant. And I also want to tell you that uppercase letters are reserved for random variables. Okay, uppercase letters are reserved for random variables. All good? Yes? Okay, next thing I want to say. What is the difference between discrete random variable and continuous random variable? Just quick one. What is the difference? If I tell you, if I use the same example, x is the score on a fair toss or random toss on a fair die. Obviously, x is a discrete random variable. X is a discrete random variable. Why? Because as I said just now, x can only take on a fixed number of outcomes. 1, 2, 3, 4, 5, or 6. Now if I give you another example, let's say y. Notice how I use uppercase this time. Y is the height of a randomly chosen person in VGC. Now, is y a constant? No. Y is a random variable because you randomly choose a person, you will get a height, another height, another height. Now, here, I want to say that conceptually, y can be measured to any degree of accuracy. Any degree of accuracy, conceptually, the keyword is conceptually. I'm not asking for using instruments. I'm saying conceptually, y can be 1.6754321 Conceptually, it can be never ending. So actually, there are infinitely many possible outcomes for y. It's continuous. Whereas for x, we say random toss on a fair die, even if we say a 10-sided die, 20-sided die, 50-sided die, it doesn't matter, there are only 50 possible outcomes. Whereas y is the height of a randomly chosen person in VGC, conceptually, y can be measured to any degree of accuracy. So y is what we call a continuous random variable. Okay, so we got that out of the way. Next, I want to talk about what is expected value of x. Maybe for this explanation, I would like to use a simple example. Okay, let's use an example. a definition of an x. Let's say, for example, I have a coin. Okay? A coin, okay, with two sides, each numbered 10 and 20. That means one coin, you see the coin here, alright? This side is numbered 10, the other side is number 20. Yeah. Okay. I would like to add as a fair coin. Okay. Alright. So, and then X be the score on one toss of the coin. Simple enough example, you toss, you get 10, toss, and then 20. Instead of head or tail, it's 10 and 20. Good enough example? Okay, simple enough. So, that's an example. What is the meaning of expected value of X? Intuitively, I think you know what is expected value of X. In this case, expected value of X is 15. Because between 10 and 20, somewhere in between 15. Now, maybe I appeal to you, let's definition this. Okay? Expected value of X is the long-term average value of X. Long-term average value. I think it's quite easy to understand. That means I toss one time, example, I toss one time, I get a 10. Another time I get a 20. Another time I get a 10. Another time I get a 10. Another time I get 20. 10, 20, 20, 20. I am not going to toss 2 times, 3 times, 10 times, 20 times. Long term, infinitely many times, and then I average all these value out. That is the meaning of expected value of X. How do we calculate expected value of X? There is a formula. Correct? There's a formula. Correct? What is the formula? This is important. The formula goes like this. I'm going to write in black, and very dark black now. Thick black. Expected value of X has this formula. Okay? Summation all X, X, probability X equals to X. Now the formula looks very daunting, but actually it's not. Let me use this example to illustrate. In this example, expected value of X, that means for each X, let's say X can be 10 or 20, right? For 10, it's like that. What is the probability X equals to 10? Because it's a fair coin, then you have half. Plus, then you have another X, you have 20. Multiplied by its probability, in this case, it is half also. Because you assign the weightage, 50% of the time you get 10, 50% you get 20, you average it out. Okay, yes, then you get 15. Now you can work on it a different way. You know what? If it's not a fair coin, where this one, example, maybe this one take up 1/3, this one take up 2/3 probability. Then you just change. This one becomes 2/3, this one becomes 1/3. Then of course the long-term average value of X is different. But we're not going to do that. We just use a very simple case. Then you get 15. This 15 is the long-term average value. It's the expected value of X. You toss it many times, you expect to get an average 15. I think it makes sense. Next, what is this meaning of expected value gx? What is the function gx? Let me use an example. Okay, let me use an example. Use this on the same example, same experiment. What is, I can use x squared plus 1. What is this meaning? This is just the the long-term average value of x squared plus 1. That means you toss one time, example. That means you toss one time, maybe you get 10. Then 10 squared plus 1, you get 101. Correct? You toss one time, you get 20. 20 squared plus 1, you get 401. Sometimes you get 101, sometimes you get 101, sometimes you get 401, sometimes you get 101, What is this long-term average value of x squared plus 1? Follow what I'm saying? Because this is 10 squared plus 1, 20 squared plus 1. Correct? What is this long-term average value? The formula goes like this. Maybe I write in black again. Not going to use this one. Okay? The formula I'm going to write in black again. Expected value of gx is actually summation g all x gx probability x equals to x. That means this, when it's useful to look at this one here, this is probability x. When x is 10, probability is half. Probability is half, right? Yes. So here I'm going to sum probability. Gx means 10 squared plus 1. The weightage is half plus x squared plus 1 times half. Then you say, hey, what is the use of finding expected value of x squared plus 1? I don't know. Maybe you want to find something, but doesn't matter. But what is important, very useful, is we will want to find the expected value of x squared. Later on we'll realize. That means long-term average value of x squared. Okay? Practice again. We want to pause the video and try to whether you can find what is the value of expected value of x squared. Okay, let's come back. You get 10 squared times half plus 20 squared times half. Okay, you will happen to get 250. Okay, then you say, oh, why do I want to use expected value of x squared? We come to the next point, variance. Before I go on to the calculation of variance, you must know what is the meaning of variance. What is the meaning of variance? I type variance measures the spread and consistency of the data. Variance measures the spread and consistency of the data. I'm sure you know standard deviation. Very simple. I'm just going to say this standard deviation is actually just the square root of variance. So if the variance is big, then the spread is big, then the standard deviation is also big. So I know you learned standard deviation before, but from now let's concentrate on variance. It basically, the values are different, but it measures the same thing. It measures the spread and consistency of the data. So let's use a formula. Okay, I introduce you the formula first. The formula goes like this. Okay, I tell you the formula, you use it, and then you just accept it for now. All right. There are two ways to calculate variance. Variance can be expected value of x minus mu square. Or you can write it as expected value of x square minus. Now the relationship between these two, I am not going to it for now. Okay, the proof is in your notes. But these two you must know. quite comfortably. Usually, we will use this. Okay? 9 times out of 10, we will use this. Sorry. 9 times out of 10, we will use this one. Okay? So, let's attempt to calculate. It's not difficult to calculate now. For this experiment we talked about, which is the toss of the fair coin, then one side 10, one side 10, one side 20, yes? Then what is it? If we apply this formula, then it's not difficult. In our example, variance of x is expected value of x squared is 250 minus expected value of x in our case was 15 square, then you get this number 25. Done. This measures the spread. Now imagine I have another coin. Use another coin. Let's say I have another coin. Okay, copy and paste. Okay. Now instead of 10 and 20, I one side 0, one side 30. And let y be a score of 1. Now, let's see. Do we think that the mean will be the same? Or sorry, the expected value of y will be the same? Yes, I think it's not difficult. Use the formula that you see above. You want to pause the video, go back and see the formula, you can go ahead. The formula says that this is 0 times half plus 30 times half. You still get 15. That means this long-term average value, sometimes I throw 0, 30, 0, 30, 0, 0, 0, 30. The long-term average value, I will still get 15. Same as the coin just now. Right? Yes, same as coin. Long-term long-term average value is 15. But if I measure the spread and consistency of the data, I use the formula. Okay, you can try it out. I don't want to go through. You realize that the variance of y, in this case, is 225. You compare this value with variance of x, which is 25. This variance of y is 225. It's a lot larger than variance of x. It means that it is not as consistent and it has a bigger spread compared to x. That's all. Okay? How you calculate? Just stick to this one and sometimes this one. This one 90% of the time you will use this. Expected value of x minus expected value of x squared. That's all. You will use that formula. Got it? Okay. Next. What is let's say I have ax plus b. A is some constant, b is some constant. What is expected value of ax plus b? Now I'm going to use another example to illustrate why the relationship works. What is expected value of ax plus b? I write down first. Expected value of ax plus b is a expected value of x plus b. Because b is a constant, can you imagine example? If x is the height of a randomly chosen person in VJC. What is 2x plus 30 cm? What is expected value of 2x plus 30 cm? Obviously, it's the same as 2 times expected value of x plus another 30 cm. I think it's not difficult. So the result goes like this. The first result I want to say is this. Alright? It can be shown, but I don't intend to show because it's quite obvious. Expected value of AX plus B is A expected value of X plus B. In this case, let's say expected value of 2x plus 30. If x is a random variable of a height of a randomly chosen person, you expect the long-term average value is 2 times the expected value of x plus 30, of course. Right? What about the variance of ax plus b? Now, first of all, I must say, remember the spread of the data, the spread. Now, if you have variance of 2x plus 30, essentially, let's not use the 2x first. If you have plus 30 to all the values, will it affect the spread of the data? That means you are asking all the students now to stand on the stool, a 30 cm stool. Will it affect the spread of the data? No, it wouldn't. If there's this much apart, they are this much apart. So it wouldn't. But I need you just to remember that it's actually a square variance x. I just need you to remember. Okay, the proof can be shown. Of course, theoretically it can be shown, but I don't think you are going to refer to the proof. But just intuitively, you know it will be the square because there is a square here. You see, there are two squares here. So it will be a square variance x. Just remember. Okay. Last bit. What if you have two random variables x and y? Now you have two. The difference between 6 and 7 is that now you have two random variables. X and y are two different random variables. Okay, x and y are two different random variables. What is the expected value ax plus by? I need all of us to remember the expected value of ax plus by is a expected value of x plus b. You just use without proof first. Okay, that is shown, you just use it first. Next one is extremely important. What about variance? You can only use this result. This one I want to stress many times. This one, only if x and y are independent. If x and y are not independent, you cannot anyhow use. Okay, cannot anyhow use. If x and y are not independent, you cannot anyhow use. So you know the meaning of independence. You learned it in probability. Okay, means x doesn't affect y, y doesn't affect x. So only if they are independent, then you say that this is a square variance x plus b square variance y. You use it for your calculation for now. Okay, that's all you need to know. All good? Okay, good.